Welcome to this explainer. Today we're going to unpack the incredibly elegant geometry hiding inside a seemingly basic, hand-drawn sketch. If you love discovering the hidden mathematical structure behind simple things, well, you're in exactly the right place.
At first glance, the image we're analyzing today just looks like a few quick lines inked onto a piece of paper, right? But what if I told you there's actually an unbreakable, proportional rule locking all these geometric shapes together? It's a really cool puzzle of ratios and areas, and by the end of this explainer, you're going to see this little doodle in a completely different light.
Okay, let's establish the basic facts of what we can playfully call the scene of the crime. First, we've got a large triangle labeled A, B, C. From that top peak, point A, a straight line drops down to intersect the bottom base at a point we're calling P. And sitting right there in the middle of that vertical-ish drop is this mysterious point D, with lines connecting it out to the bottom corners B and C.
So to solve this geometric puzzle and actually understand how all these inner triangles relate to one another, we need our primary detective tool, the area ratio property. This is a foundational rule of geometry. It states that if two triangles share the exact same height, their areas are directly proportional to the lengths of their bases. Basically, it connects a triangle's footprint on the ground directly to its overall size.
Let's actually apply this tool to our sketch. Look at the two large constituent triangles taking up the left and right sides. That's triangle ABP on the left and triangle ACP on the right. Because they both start from that bottom line and reach all the way up to the exact same peak at vertex A, their vertical heights are completely identical.
So here is the crucial point. Since their heights are strictly equal, the ratio of their massive total areas is entirely dictated by the ratio of their bottom edges. If you measure segment BP and compare it to segment PC, that exact fraction gives you the ratio of the area of the left triangle to the area of the right triangle.
All right, shifting our perspective a bit, let's zoom in on the lower section. Down at the bottom, we have two smaller triangles, BDP on the left and CDP on the right. Now, instead of reaching all the way up to A, these two share a new, lower peak at point D.
But guess what? The exact same logic applies. Just like the giants above them, these two smaller bottom triangles share a peak, and therefore they share a height. That means their areas are also locked into that exact same base ratio. The area of the small left triangle compared to the small right triangle is still dictated entirely by the ratio of base segment BP to segment PC.
And you know, this brilliantly illustrates how point P on that bottom line acts as the master dial for the whole system. Wherever point P sits, whatever ratio it splits that bottom line into, the areas directly above it, both the giant triangles reaching to A and the small ones reaching to D, absolutely must perfectly follow suit.
Okay, so we know the mathematical rules governing the big exterior slices, and we know the rules for the little interior slices, but what about the remaining shapes? What about those upper triangles floating on the left and right, ABD and ACD? How on earth do their areas compare to one another?
Well, we can figure this out with a beautifully simple piece of logic: subtraction. Think of the large triangles as your total shape. If we take the areas of those large triangles and mathematically subtract the areas of the small bottom triangles, we effectively isolate exactly what we're looking for, those upper sections.
Think of it this way. The area of the top left triangle, ABD, is simply the large left triangle, ABP, minus the small bottom left triangle, BDP. We are essentially hollowing out the bottom spaces from the whole shape, which leaves us with just the top constituent triangles on either side of that center line.
And here is the real mathematical aha moment, because both the large pair of triangles and the small pair of triangles shared the exact same area ratio, again, dictated by those bottom segments B, P, and PC. Subtracting them means their differences will also perfectly preserve that ratio. It's an ironclad rule of proportions. Which gives us our definitive geometric conclusion. The area of the upper left triangle, ABD, compared to the upper right triangle, ACD, is absolutely equal to the ratio of the baseline segment, BP, compared to PC. The base dictates the top, jumping right over that middle section. Pretty amazing, right?
Now, a really fascinating secondary mystery arises from all this. We've proven that the top triangles follow the base ratio. But what happens if we grab that center point, point D, and slide it up or down along that center line segment AP? Does that break our rule?
Let's break down the rules of point D. If point D moves up closer to A, those top triangles squash down, right? so their total absolute square footage decreases. If D moves down towards P, the top triangles stretch out and their absolute area increases. But here's the magic. The underlying ratio between the left area and the right area never ever changes.
You could literally move point D anywhere on that center vertical-ish line segment. As you slide it, the distinct areas of ABD and ACD will perfectly maintain their relative heights to one another. The total size changes, sure, but the scale of left versus right remains eternally anchored to where point P sits on the bottom base.
Oh, and by the way, just a quick aside for the geometry fans out there. That centerline segment AP that drops from a vertex to the opposite side, it actually has a formal name. It's called a savion. Understanding how savions slice up the internal areas of a triangle is a fundamental building block in unlocking way more advanced geometric concepts like Save's theorem.
So let's take a step back and look at our original whiteboard sketch. It's no longer just a few random intersecting lines, is it? You can now clearly see the invisible math binding the whole thing together. It's this perfectly balanced mathematical scale, where the position of a single point on the base forever dictates the balance of the spaces above it.
To wrap up this explainer, I want to leave you with something to visualize. Ask yourself, how many other hidden proportional rules are just waiting to be uncovered in this shape? Imagine if we simply drew one more savion, this time from vertex B across to the opposite side. How many new area relationships would that create? The deeper you look into geometry, the more the math reveals itself. Thanks so much for learning with us today.